Greetings, AP Chemistry students. Today we're going to talk about what happens in a titration. So, first of all, neutralization is what we call the reaction of an acid with a base. And as we've already seen before, these reactions generally have a K that is much larger than 1, and so they essentially go to completion because the reaction that's really happening is the H plus and the hydroxides are reacting to form water, where K is 1 times 10 to the 14th. And we remember all the way back to our intro to equilibrium, when K is very large, we assume the reaction goes to completion. And we've kind of looked at a lot of this already, but um, one key point with neutralization is that if you have a strong acid and a weak acid and they have the same pH, in order for the weak acid to have the same pH as the strong acid, you have to have more of the weak acid present in the solution. So it's going to take more of the base to neutralize it because there's more molecules of acid that need neutralization. Because if you had equal molarities of a strong acid and a weak acid, the weak acid would have a higher pH because they don't ionize as completely in solution like strong acids do. So, titration is when you react a solution whose concentration you know to determine the molarity of another solution. We have done a titration before in this class where we titrated hydrogen peroxide with potassium permanganate, and then we've been in the process of doing some acid-base titrations now. So you're familiar with the basics, but we haven't really broken it down. In a titration, oftentimes we use an indicator that changes color with pH, and we'll learn a little bit later how those work. And when you have reacted equal moles of acid and base, there is a very sharp rise or drop, depending on which way you're doing this, in the pH. And that is called the equivalence point. And for the region between 10 and 90% of the way to the equivalence point, the pH changes by less than 1.5 pH points. So let's take a look at this in a little more detail. This right here is the graph of a pretty standard titration with a strong acid and a strong base, like, say, hydrochloric acid. Your equivalence point occurs where there's this giant sharp rise and the curve changes its inflection point. So it looks like that's your equivalence point about right there. So this is about how much base it took to react with that acid. This is the pH at the equivalence point. And from the region of 10 to 90% of the way there, the pH did not change by more than 1.5 pH units. And that's generally true for every titration. Right? Now, a few key points about the equivalence point. For a strong acid, strong base titration, at the equivalence point, your pH is 7. So if this is a strong acid, strong base titration, the pH is 7. The reason that is the case is because when you have reacted all the strong acid and all the strong base, all you have in solution is water and a salt that has a neutral pH. It's neither an acid or a base because the conjugates of a strong acid and a strong base are neutral. If you titrate a strong acid with a weak base, at the equivalence point, the pH is less than 7 because at the equivalence point, you have water and you have the conjugate acid of your weak base. And if you titrate a weak acid with a strong base, at the equivalence point, the pH is greater than 7 because in solution you have water and the conjugate base of the weak acid. So if we look at this graph where we're titrating a weak base with a strong acid, at the equivalence point, if we look at our equivalence point right here, this could be somewhere like, oh, I don't know, 6 or 5 or 4 even. It's going to be less than 7 because what we have present at the equivalence point is the conjugate acid of the weak base. And if we titrate a weak acid with a strong base, then at the equivalence point, our pH is going to be greater than 7 because we have present in solution the conjugate base of that weak acid we were titrating. And I want to focus a little bit more on a weak acid titration real quick. When you're titrating a weak acid with a strong base, you form a buffer solution almost immediately because we have converted a little bit of that weak acid into its conjugate base. Now, this reaction still goes to completion because acid-base reactions go essentially to completion. You can determine the pH at any point along the curve with the Henderson-Hasselbalch equation. But what's really significant is that halfway to the equivalence point, you have converted half of your weak acid into conjugate base. So you have equal amounts of both. And if we remember, based off of the Henderson-Hasselbalch equation, if your weak acid and conjugate base ratios are equal, then the pH equals the pKa. So if we look at this graph, however much volume this required, if we go halfway to half of the volume, whatever this value is right here, pH wise, this is the pKa of that acid that we're titrating. So this is a way, without even knowing anything else about this, if you were just looking at this titration curve, you don't have to know what acid you're working with. You find your equivalence point, you go halfway to the equivalence point, that's your pKa. The same thing would be true when you're titrating a weak base, where this is our equivalence point at some volume. This is our pH, which is something that's going to be less than 7. Well, if we go halfway there, this equals the pH equals the pKa of the conjugate acid. Or in other words, the pOH of the solution would equal the pKb of the weak base. Now, another interesting thing I want to point out is this little thing that happens right here at the beginning of that titration, or if you're working with a weak acid titration, it's this thing that happens right there. This is where you are forming a buffer. So there is this sharp increase or decrease, depending on the perspective with the base or the acid, in the pH as you are forming the buffer that's present. And then along the rest of your titration curve, like this, from 10 to 90%, the pH doesn't change by more than 1.5 pH units. And you can find your pKa at the halfway point.